Everyone. So Dr. Konrad Wagstyl is a Sir Wellcome Research Fellow at the Wellcome Center for Human and Neuroimaging at UCL London. His work combines big data, neuroimaging, and machine learning to better characterize pathology, segment lesions, and predict surgical outcomes in focal epilepsy. He co-leads the Multicenter Epilepsy Lesion Detection, the MELD project, an open science collaboration to develop machine learning algorithms to automatically detect subtle subfocal cortical dysplasias in patients from around the world. So please, Konrad, go ahead.
Thank you very much. And thanks very much for having us here. It's really,
Sure.
really great initiative. I don't know how interactive things are here, but we'll try and use Menti because it's a way that we've done it a couple of times when we've run these workshops there's a couple of places where there's some questions where it'd be nice to get input from people. Although if you have any questions that aren't the Menti questions, please just unmute or ask them in the chat and I'll try and address them as we go along. So welcome everyone to the MELD project's tutorial on bringing AI into epilepsy pre-surgical planning. I'm Konrad Wagstyl, and also on this call is Mathilde Ripard, who is a PhD student in the group who's done a lot of the work in wrapping up the MELD project into a usable pipeline. And I think some of you have been in contact with her in trying to install the pipeline. So in order to use Menti, you can either go straight to menti.com and type in that code, which will be on the next few slides, or you can just take a picture of the QR code and go straight to that. So just in terms of what we're doing today, I'm going to give a short introduction to the MELD FCD pipeline, which is a free surfer-based classifier for detecting FCDs. Mathilde has made some really great videos about how to run the classifier through the test data set. I will quickly go through some slides about how to do it on the test data set yourselves. I might, depending on whether that's useful or not, we might skip ahead to interpreting the reports because I think Mathilde's video is really the best way of learning how to do that, but we'll see. And then at the end, we'll go through 2 classifier reports and hopefully there'll be 1 or 2 volunteers who could have a go at interpreting them, and then that might be a nice interactive process. So let me just get this first set of questions up on Menti and let's see if it works. So, perfect. It's working really well. Great. Thank you very much, everyone. So lots we've got from USA, Australia, Zurich, Belgium, Sherbrooke, University de Sherbrooke, which I think is Montreal. Someone joining from Australia. Well done for staying up, I guess. Cool, perfect. It's working. Fantastic. So the next question is, have you managed to install the MELD classifier? 2 yeses, that's great. So 1 person getting stuck, that is fantastic. So the biggest hurdle is definitely installing the classifier. Once you've got past that point, it is easier. So do stick with it if you have got stuck, but that's really good to know. Okay, a couple of people getting stuck. Oh, a few people. This is the hardest point, and it's because we've got dependencies that we have little control over. If you are stuck, we can try and either debug here or separately on emails after the workshop. Often every person gets stuck at a slightly different point, and it might be easier to debug one by one. Okay. And then, okay, let's next slide. And then what were you hoping to get out of the workshop? Is it just to learn about the classifier, to actually try running it live? Or to learn about how to interpret the outputs? Okay. Okay, brilliant. So I think that's it for now. Okay, let's go back to the main presentation and we'll go. So we are looking at, this is an example of an 8-year-old girl who came into Great Ormond Street. This is a bit of a motivation for the whole project. She was referred to Great Ormond Street Hospital in London, which is an epilepsy, especially a specialist epilepsy surgery center with drug-resistant epilepsy. And they suspected she had a focal lesion, but on the original FLAIR MRI, they couldn't find a lesion. And so this means if you can't find the lesion, there's potential for invasive SEG or PET, or ultimately delays to having surgery, even And if you do go and undergo surgery without a lesion, you're likely to have a worse outcome. And so the kind of whole aim of the MELD project is, can we use AI to improve outcomes in patients like this? Okay, so we're going to go back to the Mentimeter. This is an example of an FCD. And the things that we tend to look for when we're looking for an FCD are abnormal cortical thickness, blurring of the grow-out matter boundary, a flare or T2 weighted MRI abnormality. A transmantle sign is very typical for an FCD2B, folding pattern abnormalities, and then often looking at asymmetries of these features is very useful. So can we just check if we've got that?
Quick question, radiological or neurological?
So if we say right frontal lobe, we mean top left of the image. If we say left frontal lobe, we mean right.
Thanks.
Great. So I think you've all got to the right point. It's just here. Yeah, perfect. And if we go back, oh, so we've got two people on the chat. Yeah, great. Then you can see a transmantle sign. So when we look at, let's just, here we go. Someone's already answered in the chat, but what features from the ones that I was describing earlier do you think you can see in this FCD? Great, yeah. So someone can see gray matter blurring. I think that's up here. You can see this blurring in the bottom of the sulcus. And on the flare, we can see this transmantle sign. Perfect. Cortical thickening. Yeah, I would argue there. T1 pallor. So the gray being a bit pale and the white being a bit gray. Yeah. Blurring. Yes. So all of those things, fantastic. And I think that the reason for going through this exercise is one, I mean, I took you to the right section and this is a relatively visible FCD, but they're still subtle. But being taken to the right place is a useful first step, and knowing the features that you're looking for, that this looks like the features of an FCD, is also very useful. And those are kind of 2 points just to make, because when we go on to talking about interpreting the outputs of the classifier, knowing what you're looking for is kind of important. Okay, let's see what we get to. Done that. Yeah, so we've done the features. Okay, so that's the aim of the MELD project. I'm just putting up the 4 people who've done most of the coding, but it was also a massive contribution from sites all the way around the world who contributed data, surface-based data. And the objective of the MELD project was to create a large and heterogeneous MRI cohort to develop open source interpretable AI tools for detecting FCDs. And we've worked also on finding the best way of clinically translating these tools. Is it neuroradiologists, neurologists, neurosurgeons, and so on? This is an overview of the pipeline we've been developing. So what each site does locally is extract surface-based features using FreeSurfer that capture those things that we just described. So we have a blurring feature, which measures the intensity in the gray matter and the white matter and calculates the contrast between those. We calculate the flare intensities inside the cortex and below the cortex to try and capture that transmantle sign. We have a few folding features. We capture cortical thickness. So all of these are the features that we describe radiologically as being evidence of an FCD. These are mapped to a template surface, and we also run lesion masking. So this is the radiologists or researchers at each site will delineate where they think the lesion is, and this will also be mapped. So for each subject, we have the features and where the lesion is. The first step we then run is a harmonization step. So each individual in the cohort here is a point. The average cortical thickness is the Y, and the X is grouped by age, but the color is the site that they came from. And so if you look at cortical thickness, you see these big differences based on the color, i.e. the scanner that someone was scanned on changes the measured thickness. And that's a big problem if you're trying to use these features to isolate these lesions. So for the first classifier, we ran all the data through a software called Combat, and this harmonizes the data. And once you've done that harmonization, you can no longer really see these side effects, and you can roughly treat this as a single cohort. Practically, what this means for new users is that we have to have this harmonization step when you so you need to have a set of scans on which we can estimate what your scanner's doing to cortical thickness and to all these features. And typically we recommend 20, and I'll tell you a little bit more about that later on. Then in the processing pipeline, we undergo a few normalization steps. So intra-subject normalization, asymmetry calculations, so left minus right of all the features, and normalization by controls. So the first step adjusts for those age-based differences. You're removing the mean thickness so that you don't see this age level trend. And then the last two are adjusting for regional differences. So for instance, the frontal cortex being slightly thicker than the occipital cortex, you want to be highlighting what's abnormally thin or thick for that region. So having undergone all that pre-processing, we have a trained cohort and a test cohort. We split the whole MELD 600 patients into and controls into just 1,000 patients and controls, 600 of whom are patients. We split them into a train and test cohort. And then we train a neural network classifier to learn what patterns of input features make something a lesion or a healthy tissue. And once that classifier is trained, we wrap it up and predict on new subjects and create this interpretable pipeline to understand what the network is using to make those predictions. Just keeping an eye on the chat in case anyone has any questions, please do stop and ask if there's anything that's unclear. So just quickly looking at the features that we captured to make sure that they are consistent with what we expect based on the radiology. So this is a UMAP. So in a UMAP, each point is a subject and their closeness is how similar their features are. So we have intrinsic curvature, which is a folding measure. It's generally abnormal in most of the lesions. Cortical thickness tends to be increased. We have a small group who have a decreased cortical thickness down here. Almost all the lesions are characterized by blurring of the gray matter boundary. A few of the lesions are at the bottom of sulci, so this sulcal depth measure measures whether they're in a sulcus or a gyrus. And then in terms of the flare, there's a strong cluster with reduced gray matter flare and a different strong cluster with increased white matter flare, which would be that transmantle sign. So we're seeing a variety of different feature sets within these lesions, but many of them are consistent with what we'd expect based on the radiological signatures. We have an issue that we have to deal with. FCDs are very difficult to identify. They're also very difficult to mask, even if you know where they are. And one example of this is we got 10 of the patients from Great Ormond Street to be masked by 3 expert neuroradiologists. This is one example. It's a temporal lobe lesion, and the 3 maskers all pick out the left temporal lobe, but their masks don't overlap very well. So the blue mask almost doesn't overlap at all with the red and yellow masks. And what this means is when you're training a classifier, how do you deal with this? And also, how do you deal with a prediction that doesn't quite overlap where the lesion mask is, but is in the right area? And we also see this pattern emerging in the entire 600 patient cohort. If we look at where the features are abnormal directly adjacent to the lesion mask, so this is distance away from a lesion mask, and this is the average absolute Z-score of the features. So are they abnormal features? And we see that as we move away from the lesion masks, there are still abnormalities, definitely as far as 20 millimeters away, and really as far as 40 millimeters away. So we're definitely missing some of the lesions in these masks. What this means is that when we train the network, we include this ring that we don't train on because we're uncertain whether it's lesion or non-lesion. And when we evaluate the network, we also check whether the prediction was in the 20 millimeter ring, because we think that if the classifier is predicting something in that ring, it probably is lesion. Okay, so that's the kind of pre-processing. We're now training our classifier and we're running it on unseen patients. This is an example of 6 just clusters on the surface. So the burgundy is the predicted lesion, the black line is the lesion mask, and the red line is this border zone, which is 2 centimeters across the surface. The first 3 look like pretty good predictions, bullseyes, they're bang on the lesion mask, no strong disagreement. The 4th example is correctly predicted, but 1 false positive. And this is an issue with the classifier. The original MELD classifier has this issue of false positives that we're updating and dealing with now, but that's something to warn about. If you use it, you will have to review quite a few clusters. The 5th example is what we would call detected, even though it doesn't quite overlap the lesion mask. What we think here is the lesion mask has somehow not intersected perfectly with the surface, but the classifier is still picking up a lesion. And then the sixth example, it's close, but not close enough. That to us has to be considered a false positive because we can't go back to the original MRIs and check. So that's just a false positive. Overall, when we trained and tested on the full cohort, we had a sensitivity of 67%, typically picking up 2 clusters in patients, and half the controls had no clusters, and the other half interquartile range was 1, the upper limit was 1. What was really nice was that we saw that 63% of the lesions that had been considered MRI negative at some point were detected. So this is lesions that sometime in the patient's dirt journey, the MRI was reviewed and no lesion was found. And so if you had this classifier at this point, maybe it could have told you, look again in this area, you might see a lesion. Because many of you may be planning to use this, I just wanted to go a little bit more into some of the breakdowns of factors that influence detection rates, because they may be relevant depending on your center. So across adults and pediatric sites, there was a pretty equal performance. It did slightly worse in the MRI negatives than the visible ones, unsurprisingly, but still picking up 63%. One interesting thing was that it was doing worse in those that went on to become not seizure-free. And so our guess here is that maybe the lesions masks weren't necessarily in the right place on these individuals. We see an overall performance boost in the 3T relative to the 1.5T, but for some reason 1.5T and FLAIR seem to mitigate most of that. The numbers are getting quite small, so the error bars are quite large on those numbers. Finally, if we break down by histology, we're best at picking up the FCD2Bs, and the FCD1s are particularly difficult to identify. If we really restrict the cohort to kind of a gold standard of T1 and FLAIR available, FCD2B confirmed and seizure-free, we're picking up 85% of these, which is also very nice. So this is an example of one of the individualized reports, kind of compressed, that we'll go over in a bit of detail in a minute. You see on the surface where the predicted cluster is. It also is mapped back to the volumetric T1 MRI scan, so you can have a look at the predicted cluster on the brain and see where it is. And you can then also go back to the original T1 and check, does that look like a lesion? And the things that might help you make that decision, we will produce a report for every cluster of the features of the lesion. So the x-axis tells you how abnormal that feature is. So in this feature, there's a blurring of the gray-white matter boundary, and particularly a hypointensity of the FLAIR gray matter. And the color indicates how salient or important these features were to the prediction. And so this cluster was thought to be a lesion by the classifier because it had a blurring of the gray-white matter boundary and a hypointensity on the FLAIR. And as we all saw at the start, when we look at the image, we can start to interpret whether we think those features are there. So you can go back to the original cluster and say, yes, perhaps there is some gray-white matter blurring and a hypointensity on the FLAIR that looks like an FCD. By contrast, if this was a false positive, you might say, no, that looks like there's some signal dropout on this MRI. I think that's a false positive. I can exclude it from my searches. So this is what we mean by the interpretability of the report. You get to understand what the classifier used to make its decision and evaluate whether you think it's wrong or right. At this point, I just want to say that this is definitely a research tool. It's not been licensed for medical use, so it's use at your own risk and really for research purposes is the main aim. And then I'm just gonna introduce Mathilde, who did a lot of the work in wrapping this into a single script that you can then run on new patients. The script is broken down into 3 stages. The first is Free Surfer, which I think Carolina said you covered some of. It's quite a slow step because Free Surfer is quite slow. We have an option to run it with Fast Surfer if you install Fast Surfer, and that speeds this up to about an hour. Some people prefer using Free Surfer. They think the results are a bit better, but you have that time point that you have to deal with. The pipeline then extracts all the features, maps them to the template surface. If you have already run the harmonization, it will just apply the parameters and harmonize your data to the cohort. If you've not previously had a site code or harmonized your data, there will be an additional harmonization step where you need 20 scans at the start to run. This will then automatically calculate your harmonization parameters, and in future on new subjects, you just run it and we use those parameters. So that process is trying to learn maybe your flare, your temporal lobe flare, it looks lower than our average, and we'll adjust for that. It then carries out the normalization steps, and then finally runs this prediction based on the input features. Does each patch of cortex look like lesion, yes or no? And wrap that into the clustered output. This is where we think the clusters are. This is where they are on the original T1 MRI. And this is a report for each cluster saying which features were abnormal and how important that was to the classifier.
Konrad, do you mind if I ask you a question before you?
Please.
So regarding the harmonization group,
Mhm.
do you think it's better to select scans that are representative of your cohort or scans that are outliers, that have all the bias, all the movement, that are from different scanners to make sure that everything is kind of read, or included, taken into consideration?
That's a great question. So when you said different scanners, for harmonization is done per scanner. So if you have multiple scanners at your site, you would need a kind of small harmonization cohort per scanner.
Okay.
I think in general, so motion is not something you really want to be. There is a QC step that we put later on, and one of the features that we originally found was quite bad for detecting lesions you might expect is motion. So I would say you don't want strong motion artifacts because they won't necessarily be things about your scanner. They tell you more about that the person moved in the scanner. But in terms of patients versus controls, either is fine because FCDs tend to move around, so you're not going to get a systematic bias. I mean, if you have 20 controls, that's absolutely the best, but if you have patients, that's also fine.
Okay, so basically, just to summarize, if you have multiple sites, do the harmonization within site first, and then harmonize all of them again, or just
no.
with
So
within
if you
site?
had multiple scanners, you basically the way to do it would be to have a different site code per scanner. So
okay,
you just know that it's come from scanner 1 or scanner 2, and so on.
And then perfect. Got it. Thank you.
Any other questions while we're here? Happy to take.
Yeah, I want to ask one. One of the features that the reports let us know is that the intrinsic curvature. Do you think? And I know this is something intrinsic in the images, but there might be some representation in the actual MRI when you look at it.
Do you mean specifically intrinsic curvature?
Yeah.
So that's a feature that we developed to try and capture the folding abnormalities.
Yeah.
So if there is a kind of abnormal folding pattern, that's the thing that tends to pick it up best.
Okay.
So if you see it as an important feature, the thing you're really looking for is kind of an asymmetry in the folding pattern.
Yeah. Okay. Yeah. Thank you.
Great question. Yeah. Any other questions at this point? Okay. Okay. So this is the kind of details for this pre-processing, and the results can be found in the paper that came out last year in Brain. It's a fully automated and openly available algorithm with reported sensitivities of 67% and 63% if MRI negative. I'd say that 67 is on a very heterogeneous cohort. So I think that's a very realistic score on a very wide variety of patients. We've seen that if you start restricting the cohort to a single site with really excellent histology and seizure outcomes, that starts to rise as well. And all the code, as we've already covered, is available on our GitHub page. So this is almost my last slide of proper presenting before we get into the workshopy part. FCD is one cause of MRI negative focal epilepsy. There are others like HS, polymicrogyria. And when you have an MRI negative focal epilepsy, you don't always know what you're looking for. And so the aim of the MELD Focal Epilepsies project, which is our new project, is to collect a wider variety of histologies, but also the MRI scans. And so the two things we're trying to do with this is be able to detect the wider variety of pathologies. And the second is to say, if there's what was considered a false positive, it doesn't overlap the lesion mask, we can go back and see whether that is in fact a false positive or something that was missed or some other kind of imaging abnormality. And another feature that we're trying to change now is that we would like to also get the post-operative scans to say, does resecting what we identify give you a good outcome. So was the abnormality resected, and did the patient have a good post-surgical seizure freedom? And I'm raising this here because this is a great group of young epilepsy researchers. So if you'd like to become part of the MELD project, we would love to have new sites. We are aiming to have 2,000 scans in total, and we are somewhere around the 800, 900 mark. So really keen for new sites to get involved. So please do get in touch if you think you'd like to be involved in the new MELD focal epilepsies pipeline project. Okay, so this will now go through one example of a report that you might see. So at the end of running through that pipeline that Mathilde has created, it creates this PDF. And I think Javier was talking about that what you end up with is a few predictions on a surface, where the locations of those predicted clusters are, where they are mapped to the T1, and then this feature report per cluster. And I've kind of just gone through one, but this is an example of a realistic case, a few false positives, although, I mean, you can see they're all clustered around the same brain area, so they may not all be false positives. In this example, there are 6 clusters predicted on the right hemisphere. And then for each cluster, it maps it back to the T1. So you'll have a cross-sectional view of the T1. You also have a nifty volume with all of these clusters on that you can scroll through and then triangulate with the original T1. So this is one of the temporal lobe clusters, the largest one. And it as well as telling you where it is, it's this feature report that says it's on the left, the right hemisphere. It's 41 centimeters in size across the surface. The anatomical region, according to FreeSurfer, is the superior temporal lobe, or superior temporal gyrus, I think. And this feature description. And I'll just give one more example of reading it through, and then hopefully for the next one, I'll be able to get a volunteer to take us through the report, just if someone wants to have a go to see if they're interpreting it correctly. So for this example, we have decreased chromatic contrast, so blurring, and this was important to the classifier. Not much in the way of other features, maybe some increased intrinsic curvature, and then hyperintensity of the gray matter flare. And that was also important to the classifier. Okay. And the other thing that the pipeline will output that's really important to check and relates to what Carolina was asking is this QC image. And so this is a representation of the FreeSurfer reconstruction on the surface with the clusters. And what this enables you to do is check whether there's some error in FreeSurfer that is being thought to be a lesion rather than an actual lesion. So you can see for this example, the surface reconstruction in the temporal pole looks okay. This is where the cluster is. We don't think it's a problem with the scan. You might find that FreeSurfer sometimes misses half a hemisphere or something, and that would make the output unusable. And it's definitely worth checking these QC images when you're running a new patient through. So, okay. So at this point, we've got 2 choices. I could kind of take through the slides of installation. I'd say that Mathilde's videos are probably better than me describing them here, but I can quickly give an overview if people would like that. Maybe I'll look at the chat. How can I do that? Okay, so I'll quickly give it a spoken overview of how to do the installation for those, because there are a couple of people who hadn't tried yet. And I would just go iterate again, those who've tried and got stuck, let us know. Either we have a frequently asked questions on the classifier GitHub, or if you really can't find the same error there, because we have dealt with a few different people installing it now. I think we now have 35 sites who've got site codes and are running it. So there've been a variety of different problems. And if you can't find the answer there on the FAQ, then please just email us and we'll try and troubleshoot step by step. But broadly speaking, you need to have installed FreeSurfer on your Linux or Mac workstation. If you had a choice, I would tend to go with Linux, because Macs, some of them have these new M1, M2 chips that are really very different and difficult to get things to install on. You install the classifier through GitHub, you set up all the paths to download the model, and then you run the test. And this is the kind of key point: has it worked properly? Once you've got the test, following the instructions, working, you should then be able to download the tutorial data and following the instructions that Mathilde has on the tutorial YouTube, you make a note of the classifier folder, and the MELD data folder. And these are two things you then need to start running the classifier. Do we have any questions about the installation procedure so far?
I think,
Yes.
Ese, I don't know if you want to ask the question that you were, the
Oh
version
yeah,
question?
sure. Yeah, Matilda, in your video, you were very assertive that it does not work with free servers, free server 7.3 and higher.
Mhm.
Is that a flexible assertion or is it a strict assertion?
Hi, Zeke. Matilda, are you there? So
Yes.
oh yeah, do you want to answer that?
Yes, sure. Hi, Zeke. Yes, so this is a very certain assertion about how the MELD pipeline is at the moment. So I think what happened is that FreeSurfer version 7.3 has changed some way of calling some commands, and we have not adapted our current pipeline is not adapted to this new command, this new way of calling the command. And because they also have changed some codes, we have not tried how robust the results are, and if it's still giving us the same results and same results. So we cannot really. So even if you can make the pipeline work by just changing the command, we cannot really be certain of the results because we haven't tried it. So that's why we.
So just to clarify, there's two things. One, the current pipeline will break because it's expecting some the way some of the FreeSurfer functions we're calling have changed in 7.3. And the second thing is we could try and kind of point you the direction of where those things have changed. But even if you solve them, we can't really take any responsibility about how the software will work. Maybe we never tried it on 7.3, so we haven't, we can't vouch for it.
So so I cannot blame my installation not working on that. It's a problem with the processing. Is that right? So if I got stuck with the installation, it's not because of a problem with the version of FreeSurfer.
No. If you got stuck with it, but if you did get stuck, and I mean, so you've tried installing it and you've got an error message somewhere, is that right?
Yeah. Towards the conda activation MELD classifier base, I went into the bash RC. I got lost between bash and CCH. But other than that, I wonder if it's the best course of action. Do you guys know if you can get the fast surfer, an older version that your free surfer? Does that happen? Can you have both? If I have the very latest version of free surfer, can I get an older version of fast surfer?
You can I don't know if Konrad or Mathilde, I don't know if you have kind of an answer for this, but you can have different versions of FreeSurfer installed. You don't have to delete. You can have 20 if you want, there will just be different, like in the FreeSurfer, there'll be a second folder saying like 7.4 and 7.3 and 7.6 and whatever. So actually a lot of people do that, and they have downloaded the version 6 if they want to like run again some scans they had 20 years ago or whatever. So you can download as many as you want and call the one you want. So, but I don't know if you can have FreeSurfer version 7.4 and FastSurfer version 6. I don't know.
So the thing with FastSurfer is they say to use FreeSurfer 7.2. So if you want to use FastSurfer, I would install FreeSurfer 7.2 and then FastSurfer, which they play together nicely. And then it's about setting up your bash environment to point to the right folder, as Carolina was saying. So
okay,
if you want,
that's good to know that they can have more than one.
Yeah.
Right. I forgot in the FreeSurfer folder, the first thing is
the version. Yeah, exactly.
Okay. I would just be careful because I'm dealing with that, and it's always very easy to forget. Like once FreeSurfer is activated on the bash RC, it's really easy to forget to change the version if when you're changing like Studi, for example. So yeah, just be careful not using the wrong version, because if you're, for example, you're doing the harmonization with one version of FreeSurfer, and then you're just predicting some patients and you're using another version of FreeSurfer, we know that there is some viability in using different FreeSurfer version. And that's why we said that if you have one version for the harmonization, you should stick with this version for the prediction as well. But as long as you're aware of it, it should work fine.
Yeah, fair. Thank you for helping with this.
Thanks for the question. And I just to reiterate, if you start using one version, you should also probably stick with it, because otherwise that's essentially a new site, because the free software outputs start to look a bit different between versions. So fix the version. Okay. So Matilda's made really great step-by-step videos for installation, harmonization, and prediction, which I would encourage using these as guides. They're really nice and clear. I don't think necessarily going through. I won't go through this step by step now, because this is really Matilda. This is what's covered in your demo, isn't it? Yes.
Yes.
In the tutorial. So I will. Essentially, you need to move you download the MELD data, you move it into your data path folder, and you organize it as step by step following the instructions. I won't read them out one by one to do live, because I think that won't work. But so I will skip ahead now to looking at so harmonization. This is the first really important step. This is an example of what happens with a new reference site. So we've harmonized our MELD data. This is the gray. All the MELD data now looks like it comes from one site. We see a nice age-based trend and no more site-based differences. And we add a new site, which looks like the red points. And you can see that it doesn't fit within the distribution. So the first thing we do when we have a new site is you need to estimate these harmonization parameters. And these are the things that will move the red points to be fitting within the gray cohort. And using Combat and those first 20 scans, it estimates these parameters, adjusts your thickness values. So in this case, it makes them a bit thinner, but it'll do something according to the spatial map of those thickness values. And then the red points now look like they fall within the entire MELD distribution. And this is what enables us to run our machine learning algorithm on new unseen data. So before you run on a new patient, you have to have done this harmonization. And that step-by-step procedure is covered by Matilda's harmonization video. So the steps you need to do that is first get a site code from us. So you email us and we'll send you a site code. This is because each site has a unique code that will be stuck with your harmonization parameters. And then when you run new subjects, it'll look for that site code and look up the harmonization parameters and apply them. If you have a new scanner, you would need a new code, and then you point towards the correct. That would then automatically harmonize for that scanner. So when you run the new patient pipeline, you run it with your site code, which in this case would be H5, with a list of the IDs, which points you towards the 20 or however many harmonization IDs you have in this ID file, and a demographic file, which will have both age and sex. And so this keeps the age and sex effects, but removes any of the sites effects. Once you've run this once, instead of IDs, you can run it on single individual subjects and just predict, rather than needing to run it on multiple subjects at the same time. Are there any other questions about harmonization at this point? Okay. And then now you have the harmonization done. As I said, you can run it on a single subject. So run new patient pipeline on a new site, on your new ID, and this will then run through the pipeline and produce a prediction report. And so to find the reports, you go inside the outputs folder in your data directory, into the prediction reports, into the subject ID, and there you'll find this patient report PDF, which we'll now go through. Oh, is that a question? No, just unmuted. Okay, so let me just get them up. Okay. So I will get the patient report up. Does anyone want to have a go at kind of describing what they see on this report? A couple of people said they wanted to practice interpreting these AI reports. So could we have a volunteer?
Happy to volunteer.
Oh, great. Okay. So do you want to kind of have a go at taking us through, and I'll scroll slowly while you describe what you see.
Yeah, it looks like one participant was put through the pipeline and it detected one cluster.
There.
The cluster is on the right hemisphere. Yep.
Hello? You
I see-
Walter?
oh,
Oh, someone has I will try and mute whoever that is. Okay, carry on.
So that one cluster, we're seeing it now projected into the patient's brain anatomy. And as you can see on the red box, it's on the right hemisphere. It's a small cluster of 1.3 centimeters square. And per the atlas is located in the rostral middle frontal. And the cluster was classified as such mostly because of an increase in the intrinsic curvature. That seems to be the most salient feature, and perhaps some increase in the so-called depth.
Fantastic. Thank you very much. That was great. That's really great. Very clear. That's exactly, yeah, perfect. Great. So I guess in this case, you'd go back and look at the T1 and say, I mean, the only thing the classifier is picking up here is a subtle folding abnormality. Does this look like it could be a folding abnormality, or perhaps on the QC image, it looks like a reconstruction error that looks like a folding abnormality. But yeah, we can't do that here. You have to have the original T1 for that. Great. Well, we have one more example report. So
I have one question before you, sorry. So how would you interpret the feature results if the combat versus asymmetry versus normalized bars are opposite and are significantly up,
Great question. Yeah, we've been talking about this. So what we tend to see is that if there is an abnormality, the normalized and the asymmetries will both point in the same direction. So in the examples I've shown, I'm pretty sure that's always the case. The combat, I think in future versions we will stop showing this, because the combat basically means it hasn't undergone any of those pre-processing steps. So like thickness could be thin or thick, just depending on the region, or the flare could be, it could be a myelinated area or a not very myelinated area. And so here it's pointing in the opposite direction. For, it looks like this high flare, but it looks a bit low for the cortex. So I mean, the saliency will really tell you what was important, and hopefully that can guide the eye. And in future versions, we'll be dropping out the combat.
Okay, good. Thank you.
Great question. Okay, so we have one more report. If someone would like to have
And Konrad, quick question. Sorry if I missed this. You guys probably said it, but so you have to enter both the flare and the T1 into the pipeline?
Great question. No. So we accept the T1 is the minimum scan, the 3D T1. You can have no flare. It will just run without the flare, and there is a small cost in the performance of the classifier, but it will still run and produce a prediction if there is an abnormality. So this is an example report of no flare, of a patient with no flares, actually. So that's a great question.
Perfect. So for the harmonization, are you harmonizing on both the T1s and the flare?
We do it's a good question. If you don't always collect both, what you should do, because free surface sometimes uses the flare to help with the segmentation. And therefore, if some of your patients have flare and some of them don't, it's almost like they're two sites, because the thickness will be all off for, like, there'll be systematic differences between how they were reconstructed. So that is to say, I would treat, if you have just the T1, if you have some patients with just the T1s, that's one group, and then T1 and flare is another group.
Yeah, sounds good.
Okay.
Konrad?
Yes.
May I ask something? How does the pipeline do with motion? I guess not very good.
So we don't have the original scans. It's quite hard to say exactly how it's doing with motion. I mean, free surface is notoriously not great with motion, and things like thickness start to get messed up. There are scans with motion that we're picking up the right areas, but it's generally the noisier the scan, the harder it is. And in our first piece of work, which is now back in 2016, when we had the scans, this was just done on Great Ormond Street, we had 30 scans in total, so it was quite a small data set, but we blindly rated scans for motion artifacts, and that tended to be the biggest predictor of missed lesions. So in short, it's not very good, but I think also the human eye is also quite struggles with motion artifacts. Yeah, good question. Okay. Perfect. So would anyone like to have a go at describing, this is an example of just a T1 prediction. Can we have a volunteer to describe this lesion? Don't be shy.
wants to try, guys?
Is that you volunteering here?
I mean, I can do it. Yeah, of course. No problem.
Okay, fantastic. Thank you.
Yeah, this is a report of a patient with no flare. And then it's also it's a one cluster that was found. It's yeah, in the frontal region. We'll see. Yeah, it's in the right frontal region. Actually, it says that it has a size of 4.41 square centimeters. It says I said superior frontal, but here, like unlike the previous case, the gray white matter contrast is important. It's a feature that has a huge impact in the classifying process and also the intrinsic curvature. But yeah, it is what it says, and it's yeah, in the right superior frontal gyrus actually. Yeah.
Perfect. Yeah, and there's a small
yeah, and the cortical thickness as well. Yeah, indeed.
Right. And just as that's great. Thank you very much for volunteering. And just to clarify, so when you don't have flare, you just don't see a flare output. The classifier it's kind of designed to just it will hopefully ignore the lack of a flare and not produce any predictions for flare features because they aren't there. So this is what happens if you just have a T1. Great, thanks to volunteers.
Good question.
Yes.
This might be. I mean, I should have asked this at the beginning, but this is just for post-surgical MRIs, right? You cannot use. It's not validated for post-surgical MRIs.
Very good question. So one of the ways we've been trying to use this is with clinicians so sometimes they give you patients who've been operated who continue to have seizures. We would always recommend going back to the first scan.
Okay.
Because
tons of it,
and surgical resections don't play well together. Yeah.
Okay, good. Thank you.
Yeah. Okay. So last 10 minutes, we've done the 2 example reports. This is exactly where we start to exactly what you're talking about. So if we go back to, hold on, where are we? Yes, here we go. So if you go back to this menti.com, the code was here. So it's 58904711. And the question is, if you were to use the classifier at your own site, how might you do this? Would this, which patient group would you be thinking of applying this to? And maybe what, for example, well, I'll see if people can provide answers. Then we can discuss some of the ways that we've tried using it. Great, MRI negative. Positive. Lots of good suggestions here. So lots of suggestions around MRI negative, drug-resistant epilepsy, older children. That's a good point that I hadn't mentioned explicitly, that so far free Cepheid doesn't work for anyone under 3. So 3 and older, it's been tested on, but hasn't been tested on anything less than 3 years old. Discordant data, focal epilepsies with good quality scan, but no evident lesion, MRI negative, PET and SPECT positive. Fantastic. Okay. Large lesion, which needs surf. Do you mean for the extent for the large lesions? Yeah. So you can use them on FCD positives, and a lot of sites that have started to use it first want to validate it on some known FCDs just to understand how it's working for them before they then go on the MRI negatives. So large lesion which needs surgery, and that's another use case that has been in our experience. There are a few cases where the extent of the lesion wasn't clear on the scan, but the classifier gave a boundary that made them reevaluate their resection margins and extend the resection. It was in a temporal lobe lesion. They extended it back a little bit. So nodule pathologies, no stroke, for example. This would be, I guess, I wouldn't use it where you have a very obvious other pathology. I mean, you can talk about FCD3s, which is an FCD plus another pathology. And in theory, this classifier has been trained in them, particularly the HS FCDs, but it becomes a little bit difficult to interpret. So at your risk, I would say, and particularly if there's quite a large deformation due to the primary pathology, your risk is that free surfer won't deal with it very well and you'll get false positives around there anyway. Okay, that's really great. Thanks for those answers. Why's that stuck on my screen? Anyway, oh, someone I think has commented on Zoom. How's that worked? I've got this blue text, but let's ignore that. So examples that lots of people gave, MRI negative patients. Some of the cases, some people who, when we asked the MELD sites, have been using them on all MRI negative patients. And I would say that there's a risk there that if you think it might be an HS, it seems not that useful to put it through an FCD detection pipeline. So when we've tried it on all MRI negative cases being considered by the MDT. We've also tried it with the radiologists who've said anyone they suspect of having an FCD. So that means MRI negative, but there's other reasons why they think it's an FCD. And that's been a very effective way of using it. The problem with this kind of blanket MRI negative is sometimes you're not really suspecting an FCD and then you don't know what to do with the prediction when it comes back, because sometimes there are these false positives. And as I said at the bottom, there have been a few groups who've been doing it on research cohorts for the retrospective analysis, and that's been working well for them as well. Great. And someone said resection extent, which is another nice example of how you could use it. So I think that we're coming up to an hour, so I'm going to stop in case this to give us some time for questions. The useful links hopefully were sent in the emails. The classifier is the key one. The paper describing the classifier is available at Brain. We have these fantastic new video guides that Mathilde's been running. If you are trying to install it, and really, I encourage you to push through that barrier, because once it's installed, it does keep working. We've had people who've been using it for several months now, with positive feedback. So if you do really are stuck, if you can copy out whatever the error is that you're getting and send it to us, we'll try and debug with you. And I just want to quickly thank everyone involved in the MELD project. This is all the sites that contributed data the first time, and particularly the people involved with coding, the co-lead Sophie Adler, and Mathilde and Hannah, who did lots of the coding. And thank you so much for inviting us to kind of present to you. I will now might be a moment if anyone has any other questions.
Thank you very much, Konrad. I do have one question. Well, one comment. It's like we know that the distribution, the brain distribution, FCD is not the same. Like you don't have the same likelihood of having an FCD for all the brain regions. So this is something that might help you. Like if you have an MRI negative, but for example, the semiology, seizure semiology points to the frontal region. For example, this patient has night seizures, night hypermotor seizures. Probably you might think about an FCD, especially if this patient has very frequent seizures. Or you can see some electrographic pattern in the EEG. So this might be another tool that might help you to determine whether this could be a good option to try to find an FCD in your patients.
So just to kind of add to that, we have these 700 lesions. We mapped them all to a surface, and you can see, I think this is what you're talking about, the fact that some regions are much more likely to have FCDs than others. Is that what you meant?
Indeed, yes.
Yeah.
Yeah, because most of the time you see it in the frontal lobe in some patients, and in some other patients next to, for example, hippocampal sclerosis, or some other patients in the temporal lobe.
Yeah. So temporal lobe and frontal lobe are by far the most common. And if, as far as this is useful, this map is available in our epilepsy publication. And I agree, if you have a suspected frontal sulcus lesion, you're much more likely to think that's where it is than in the occipital lobe. Yeah. Yeah, it's a good comment. I think
yeah.
Karina, you want to go? Okay, Konrad, I was just wondering if you had any reports handy with false positives. You showed us one with 6 foci, just to see what to look out for in terms of false positives.
I'll have a look.
Meaning, are they obvious? You know, like, is it easy to say, oh, that's clearly a false positive?
So, I mean, I don't have one to hand. I don't know if while I'm answering the question, Mathilde, if you have one. I don't know if you can. Okay, Mathilde's nodding, so I'll just quickly. So first of all, you tend to get false positives being of 2 types. So one is false positives in the sense that you can get multiple small clusters within the lesion, so they're not kind of annealed, and that's quite easy to deal with. You can see that there's 5 clusters, they're all in the temporal lobe. In fact, that's probably mostly all lesion. In terms of filtering out other types of clusters, often you have a clinical suspicion that it's a left or a right or a frontal and that can help remove it. Beyond that, the lesion reports can be very helpful. I'm trying to think if there's a particular pattern with the false positives that make them easier to filter out. I don't. I mean, Mathilde may be also able to help a little bit more because she's talked through a lot of these with the MDTs. My impression is that the clinicians are quite good at discarding false positives, but I guess the hassle that we're trying to deal with is there are a number of them, and we're now trying to remove. We have a new version of the classifier that'll be coming out sometime later this year, which has dropped that false positive rate massively because we think it is a problem that we prioritized. But I'll let Mathilde, if you have any comments on that as well.
So I can share a report that we have of false positive that we know for sure have false positive there. But it's mainly false. I mean, it won't be like, it will be one example among like other example of false positive that we have, that you can have. So, sorry, it's a bit hard. Yes. Yeah. Can you see my screen? So this is an example of one report that we have at Gosh, so at Great Ormond Street Hospital in London, and you can see that we have like 10 predicted cluster. And when we look at, for example, some of the cluster, I'll just go down. Sorry, I'm connected remotely, so it might be a bit slow. Yeah, we can see that a lot of the FZS silencer are predicting, like, for example, an hypo intensity of flare, a flare hypo intensity, where when we would mainly like expect like a hyper intensity, for example, or like an increase of the cortical thickness when we would expect like a reduction of the thickness. So here we know that this is mainly artifacts due to flare artifact that we have on our sequence at Gosh specifically, because when we rerun this without the flare sequence, we have like most of the false positive removed. So this is one example, but if you have an artifact due to, for example, the free surface segmentation, what we could expect will be like a very high interesting curvature that goes really beyond even the scope of this plot, or this kind of like very obvious abnormalities. And one way to tackle this is to open Freeview and open the prediction and open the T1, open the PIAL and the white surfaces, for example, and look if there is no abnormality or segmentation error where your prediction are. And we actually, I think, Konrad, you showed it, but I'll
show it one more time. If you stop showing, I can share again.
So there is a script for doing that to check this.
So here, this is a QC script that comes as part of the package, and thanks for raising that, because I didn't cover this in much detail. If you run this on a script on ID, it will automatically load up with FreeSurfer the inner and outer surfaces and the predicted clusters, and that helps you check whether this is a kind of a recon error, potentially a flare artifact. And as Mathilde said, we found out that the sequence at Gosh tends to have these particular consistencies. So maybe one lesson from this example is that if you run it on a few of your patients, you might start to see patterns of things that are being picked up as false positives. And I guess that's partly just to do with the variability of scanners that we haven't been able to completely account for. But that's a great question. And I think,
can I comment? I'll give a quick comment. So it's really interesting because before you answer the question, I was thinking it's probably because of the flare or the region. So we just submitted a paper that compares the reliability between the FreeSurfer outputs between just using the T1 versus the T1 plus the T2 versus the T1 plus the flare longitudinally. So we had around 600 images and we scanned them 3 times, like the 3 scans 3 times in kind of consecutively every like 1 or 2 months. And actually the reliability for the thickness measures from free surfer dropped massively when adding the flare. So the highest reliability was just using the T1 or the T2, the reliability both within session and across sections like longitudinally was above 0.9. Whereas for the thickness and for volumes, it was just high for everything. But for the thickness measures, when we use the flare flag, the reliability dropped to like 0.6. It was kind of wow. So yeah, I mean, I guess we can talk. I can send you the paper once it's out there, but maybe it could be related to the flare, to the reliability.
Absolutely, could be.
Yeah, and actually, based on that, we also compare it to like this is out of context, but we also compare it to a 7T, and I actually got in touch with the free surfer author, like Enrique Iglesias and all those, and they were aware of this error, and they said their comment was like that free surfer kind of not values, but like aims for specificity, for sensitivity, sorry, aims for sensitivity and not specificity. So, and that's why in like when you add the T2 or the flare, it could show you more like different values compared just only to a T1 because it's kind of more sensitive, obviously. The interesting part was that with the flare, the thickness were thicker compared to a T1. So it's less reliable, but thicker. So just, you can kind of add these to your reasoning whenever analyzing all this. But yeah, just for you to have in mind that maybe these, including the flare, maybe it will be interesting to see what happens if I just use the T1 or both. Yeah, but
that's interesting. Thanks for sharing that. Yeah. So I guess flare causes some false positives, but on the other hand, is a very FCD feature. I think
Jose had.
Yeah, I think one last question.
Yeah.
And we should let people.
Thank you very much.
Thank you so much for being here with us. I just have one question. I know that this pipeline is designed specifically for detecting FCD, but have you encountered any case of mild malformation of cortical development with oligodendroglial hyperplasia, what we call MOGI?
Have you
encountered any of that?
So that's a great question. I think when we collected the data set, which is finished collection in 2018, I'd say that MOGI was still a kind of emerging phenomenon. So I suspect in the FCD1s, we have MOGIs, because before that, they would have just been called FCD type 1. So we don't know for sure, but we think they are probably in there. And we are really aiming to get some of these MOGI cases for the new FCD pipeline, the new focal epilepsies, so that we can specifically detect them. Yeah.
Thank you.
Okay, I think it's time to wrap up, and I would like to thank Konrad and also Matilda and all of you for being here, and Carolina for directing.
Thanks very much. Thanks for having us here.
Yeah, thank you, Konrad. Again, it was amazing. And again, for all the people listening, just in case you have images, just feel free to get in touch with Konrad. And if you want to be part of the MELD project, it's a great initiative.